The coefficient table, here's where we see those individual player stats. In this case, it's the individual player stats for the regression coefficients, for our predictors. So we're able to see for each predictor, are they having a significant effect or not? We see mother's education. Here's mother's education. The unstandardized coefficient, B, is 0.113. The standard error is 0.020. The standardized coefficient is 0.309. So this is 1 year of education. How many grade points do you go up? 0.113. This tells you if mother's education increases 1 standard deviation, grades go up 0.309 standard deviations. The 0.113 is 1 unit increase in education, 1 year's education. Grade points go up 0.113. So again, same thing, they're just, are you talking years of education and units of grades? Or are you talking standard deviations of education and standard deviations of grades? Because it's the same thing either way, the t-test is exactly the same. It's just, are you speaking French or are you speaking German? You're still saying the same thing. Remember the t, how do we calculate the t? Is the unstandardized coefficient divided by the standard error. That was how we calculated t, I think, the second week of class. So 0.113 divided by 0.02, this is where if you do the math, it's not going to come out exactly 0.5551. But that's just because it needs a little, we need a few more decimal places to make it work. But it does. This divided by this gives you the t. What's our degrees of freedom? Remember, it's not on here. We have to, well, we know the degrees of freedom is 395. It's kind of there as a clue. But you have to go back to the ANOVA table. In fact, gosh, thinking about it, when you look at the ANOVA table, maybe just write down somewhere what that degrees of freedom residual is, because you're going to need it when you're doing your t-tests for the regression coefficients, or when you're reporting the t-tests. Because if you write up your thesis and you just say t equals 5.551, the reviewer, your advisor is going to come back and say, no, if you didn't follow the formatting, you have to tell me the parentheses and the degrees of freedom. So mother's education, B is 0.113. The t with 395 degrees of freedom is 5.551. P is less than 0.001. School quality, our regression coefficient B is 0.042. T with 395 degrees of freedom is 2.453. P is equal to 0.015. And for us, I like writing exactly what the P is. We're not going to do the P's less than 0.05, P's less than 0.01. Only when it's P's less than 0.001 then we don't know what it is. But otherwise, always write the exact P. Part of the reason, to be honest, I think that we ended up with the whole P's less than 0.05 was because we didn't have calculators. You didn't have computers. So you have to look up a number. You couldn't have a table. You could have a whole set of encyclopedias that had every set of degrees of freedom with all the different possible values of t-scores to come up with exact values. So it was just easier to have one table. You have to pick some, for different degrees of freedom, what's that critical t-score? And they just decide, 1 in 20, 0.05. And I think it's just kind of a whole leftover of, or some of it. Some of the reasoning why we say less than 0.05, less than 0.01, less than 0.001 is a leftover to using tables. If you can report the exact value, just give the exact value. That's my philosophy. Some might disagree. But for us, that's what I want. Okay, so this is how you'd write it up. If we were talking about, is the effect of mother's education significant? Yes, it is. Look, and how significant? 0.113, and here's my test statistic, and there's the p-value. We can also calculate confidence intervals. Right? Remember, we learned how to do that. We can do a 95% confidence interval, which if I don't tell you otherwise, we can always assume we'll do 95% confidence intervals because we're doing an alpha of 0.05. You want your alpha of 0.05 to line up with a 95% confidence intervals, and then your conclusions will always be the same. To do the 95% confidence interval, we need to know our unstandardized regression coefficient. We need to know the standard error. And we need to know that critical t-score. What's the t-score where 95% of the sample is in between? So we have look back on the slides, have the little script for doing that. So if we go to Excel and we type in to get the t-score, where it's plus or minus that t-score gives me 90.95, we see the critical value is 1.966. So again, for a t-distribution with 395 degrees of freedom, because it's a t-distribution, you have to tell it what the degrees of freedom are because this shape changes based on the degrees of freedom. So for 395 degrees of freedom, 95% of the t-distribution is between positive and negative 1.966. So once we have those three numbers, we can calculate the 95% confidence interval. To do that, we just plug in, we follow the formula, the B in blue, look, I color-coded it, blue, 0.113, plus the critical value times the standard error. So it's 0.113 plus or minus 1.966 times 0.020. 1.996 times 0.020 is 0.0393. 0.113 plus or minus 0.0393 gives us 0.0737 at the low end up to 0.1523 at the high end. And kind of as a practice, I think there's more variability depending on the discipline. You'll see that in brackets as the confidence. So kind of reported like this, 95% CI equals, in brackets, 0.0737, comma, 0.1523. That's just saying, the comma is just a way of saying, here's my low, here's the high, somewhere in that range. That range is the 95% confidence interval. And we could talk about that as the most common way I think you hear people talk about it is, I'm 95% confident that the population value is somewhere in that range. That's whatever that means. I mean, I'm not, I'm 95% confident. You can think of it again, the technical answer is, if we did this an infinite number of times with an infinite number of samples and we all calculated different 95% confidence intervals, 95% of our 95% confidence intervals would contain the population average. So it gives you a sense that 95% of the time it's going to be in whatever range you report. Not necessarily this range, but whatever range you report, 95% of the time the population average is in there. And it's useful just to get a sense of how accurate the effect is. It's pretty, it's not huge. It'd be interesting if the range was grades of -2 up to +4. That'd be kind of a crazy size range. But it gives you a sense of how precise is this 0.113. Is it very close to this? Or could the real value be much different? It's a nice, good indicator of the precision of our estimate. I like framing it that way. Yes. This is a point estimate. The 0.113 is a point estimate. That's saying this is exactly what I predict, even though we know it's probably wrong. This is an indicator of how precise we think that point estimate is. because it doesn't overlap 0, notice the low end is still a positive value, the high end is a positive value. So if you think if we put these on a number line, 0's here, the range is all on one side. It doesn't overlap 0. That tells us that we're confident the population value is not 0, because 0 is not in our confidence range. So if you were doing hypothesis testing, you could use this and say, oh, you look at this and you know, oh, they rejected the null, because it doesn't overlap 0. If, on the other hand, 0 is somewhere in that range, then we can't be confident that the value is not 0, because we've just said, I think the value could be 0. So in this case, it's clean. We're not surprised, because we already saw we rejected the null. We saw the p-values less than 0.001. So we're not surprised. In fact, you know you've done something wrong if this included 0. There's some math error somewhere. Okay? Are we good? This is simultaneous regression, multiple regression. Again, simultaneous because we just threw everything all in, all simultaneously at once. Clean, straightforward. Notice we're not arguing about which comes first or which comes second. We're not, it's not much to debate about other than do we have all the right variables in. The cons, kind of the downside, it doesn't consider indirect effects, which we'll talk about more in a minute, why that might be a problem. And like all of the approaches, you have to make sure, well, the results will vary depending on the variables in the model. If you have the wrong variables in the model, you'll get the wrong results, but that applies to all of them. And even though we're not looking at a causal model, you still have to have the common causes of anything that's of any of your important variables. Any variable that you're really going to point to, you have to make sure the common causes for that variable have been included in the model, or else you're going to risk misstating the results. Okay? Next, we're going to